Good evening, ladies and gentlemen. So, here it is, the most famous, the most powerful, but most of all the simplest equation in the universe. There is no galaxy so distant that it does not apply here. On the other hand, it is also one of the most controversial. People, by which I mean physicists, constantly argue about its meaning. I have been involved in those arguments and I know whereof I speak. E is not the problem. Everybody accepts that it stands for energy. M is not the problem either. It stands for mass. C is where the whole thing falls apart. It stands for the speed of light, or celeritas, or constant, or something else, starting with C. What is the speed of light? And how do you square it? Obviously, to square it, it has to be a number, or possibly a brick. But we're talking maths here, so it has to be a number. But which number? Speeds are measured using two factors. Some define length and a unit of time. The time is always measured in single units, so numerically just 1. 30 miles an hour is a good example. With that speed, you cover 30 miles in a single hour. Even if we only use units we're familiar with, this makes the numerical value of c squared somewhere between 1 in light years per year and just short of a quintillion feet per second. In case you're wondering, a quintillion is a billion billions, or to be more precise, this, which is just short of that. Bear in mind, there is nothing to say we have to use existing units. We're free to make up anything we want at this point. I tend to use Schnurgles per fluid, which keeps everybody on their pedal digits. More to the point, there's nothing to stop us using fractions. It could be anything, really. Fortunately, we can go back to the source to see what it was originally supposed to be. In 1946, Einstein was not a happy bunny. Of course, like most people, he was delighted the war was over, but it was his part in how it finally came to an end that troubled him. Hiroshima and Nagasaki weighed heavily on him. In Oppenheimer's telling phrase, he too had become a destroyer of worlds. So, when Science Illustrated in the US asked him to write an article explaining E equals mc squared to ordinary people, you and me, he leapt at the chance. And the title he chose for this article, The Most Urgent Problem of Our Time. At this point in his life, he was most concerned to convey the destructive power of nuclear forces. E still stood for energy and M for mass. In his precise words, E is the energy that is contained in a stationary body, M is its mass, the energy that belongs to the mass, M, is equal to this mass multiplied by the square of the enormous speed of light, which is to say, a vast amount of energy for every unit of mass. Just to give you an idea, it has been calculated that the amount of mass used in the destruction of Hiroshima, the mass deficit, was around 1/100th of an ounce. And yes, that is his writing. I'm fairly sure this was the first time he wrote the formula that way. So, you do not need to be a mathematician to know that c squared is not 1 then, or for that matter, 2.5. Enormous and vast pretty much guarantee it to be a big number. For c, Einstein himself in the article used 186,000, already familiar to his readers as the number of miles light travels in a second, which gave him a ratio of 34 billion to 1, and that could have accounted for Hiroshima. While we're on the subject of 1, just in case there are any physicists still here, c is one of the natural units, all of which by definition have the value 1, making them units, as you've guessed. This is perfectly legitimate. One just counts the units of time, not of distance. You have to keep track, but it saves writing out long strings of numbers every time the speed of light comes up in the calculations. Also, if c equals 1, then c squared equals 1, so mc squared just equals m. That makes E equal m, which introduces the idea that E and m are really two states of the same thing, which is now generally accepted, if not entirely understood. It makes the next bit a little bit clearer if we divide both sides by m. See, it's all coming back to now. This goes into this number of times. I've always said it was simple. Now we have the easy ones, E and M, on the same side. Essentially, E is the unbound state of the energy implicit or contained, as Einstein put it, in a unit of mass, which we might call its bound state, to coin a phrase. To the left of the equal sign, we have what is called a ratio, and to the right, the size of that ratio. And by the way, this ratio is valid for all values of M without exception. Now, you can have a ratio of any two things, of ducks and tractors, for instance, but you usually have to explain the nature of their relationship, why they're being compared. However, when the ratio is between two aspects of the same thing, ice and water say, the ratio is expressed as what is called a dimensionless constant. A dimensionless constant is what you and I call a number. 3 is a good example. You can use it wherever you want, in any circumstances or conditions throughout the universe, so long as there are 3 of them, whatever they are. C squared is just such a number. That is the ratio between the binding energy of the nucleus in the bound state and the energy released when it is unbound. It also does not vary. That's why it's called a constant. We know this partly because Einstein says it is so, but mostly because the bombs all work. It would be useless if bombs sometimes went kaboom and sometimes went. It is militarily unsound. That's not nuclear deterrence, it's unclear deterrence. Please yourselves. Or perhaps a better example is nuclear power stations. We can't have them sometimes going kaboom. That's just antisocial. We also know it is a number, dimensionless constant, because the Stanford definition insists on it. According to Einstein's famous equation, E equals mc squared, the energy E of a physical system is numerically equal to the product of its mass, m, and the speed of light, c squared. The key word here being numerically. Still, how can we know what the speed of light actually is, given that it could be any number at all? The answer, as Einstein himself pointed out all those years ago, is through experiment. We can't guess what the speed of light is, but we can know what the ratio is, and then find the square root. His only problem with that was that if you tried to add energy to increase the mass by, say, heating it, the enormous speed of light would work against you, and the required heat would just obliterate the mass. Nonetheless, nowadays, or more precisely in 2005, the anniversary of Einstein's Annus Mirabilis, when he did most of his great work, Rainville et al. Were able to devise and execute a direct test of the ratio by comparing the mass deficit of a dislodged neutron to the energy of the gamma radiation it produced, and it agreed to within 4 millionths of a percent. That's 4 parts in 10 million. Amazing, no? Wait a minute, I hear you cry. Agreed with what? To within 4 millionths of an ujar. And this is where the story really starts. It agreed with the square of the speed of light as measured in meters per second, 2 factors we invented. That's the amazing coincidence from the beginning of this. Forget about the speed of light for a minute. I find it hard to believe that we, the human race, careening about on what is officially, at least according to Carl Sagan and Stephen Hawking, an insignificant planet of a humdrum star lost in a galaxy tucked away in some forgotten corner of a universe, that we, on that planet, have the power to specify the ratio of binding to unbound energy in the nucleus of every atom in the universe. Identify? Yes. Specify? No. And if we didn't specify it, then it has to be one hell of a coincidence that randomly and inaccurately measuring our insignificant planet has produced the identical number that it took the universe a Big Bang and 14 billion years to produce. Some big number, sure, but this one, of all the numbers in the universe, this is the least likely number for Rainville et al. To have come up with which to have come, as Churchill would put it. Time's running out, but for those who are wondering how we actually ended up with our number, Here's a swift summary. Our number is the square of the number of meters that light in vacuum travels in a second. That's almost 90 quadrillion, by the way. We got the second from the Babylonians, or more accurately from chickens being farmed by Babylonians, while the meter was a direct, if inaccurate, product of the French Revolution. Let's start with the second, that is the former. Fond though we are, we have to face the fact that we live on an inhospitable planet, or at least one with a highly corrosive atmosphere. Everything from bridges to blueberries left out in the rain rots. That, and the fact that most living things are quite squishy on the inside, means that they all have some sort of skin or shell to keep them together. I think we can agree that the market for half a fresh egg, or even a third of a lemon, outside a gin and tonic, will always be small. This led the Babylonians to become interested and eventually fixated upon numbers that could be easily divided up into integers. 6 is a perfect number. No, I mean that's the technical term for 6 is perfect. A perfect number is one that equals the sum of its divisors. Augustine, Bishop of Hippo, was so entranced with the number 6 that he believed that God took 6 days to create the universe because 6 was so perfect. Then, of course, he took the day off and spoiled it. But not for Augustine, who remained an enthusiastic supporter. Back to the Babylonians. Like the Romans and us, the Babylonians counted in tens, but in groups of 60, with units up to 9 on the right, then 10s, 20s, 30s, 40s, and 50s on the left, up to 59, ending in a symbol for 60, then starting again in the next whole column with 61, and so on. Obviously, anyone who likes 6 is bound to love 60 and adore 360. That's why a circle has 360 degrees of 60 minutes each of 60 seconds. Ptolemy, the astronomer, was the first to use those terms, and they went on to designate divisions of an hour, of which we have 24 per day. That was bound to happen, sure as eggs is eggs. Bear in mind that there are 86,400 seconds in a day on this planet, but they have to be measured at sea level to avoid time dilation, which almost certainly means no other planet in the universe has a second the same length as ours, always assuming it had its own Einstein, which is improbable at best. Talking of time dilation, we know that the mathematics Einstein was using works because all sat-navs allow for time dilation to get you to your granny. If time dilation was not true, you'd never see your granny again. And it's Christmas, so it must be true. The meter is a product of the French Revolution, along with hectares, litres, grams, etc. In the immortal words of the Marquis de Condorcet, their work was to be for all people for all time. The Académie des Sciences established a commission chaired by Jean-Charles Chevalier de Bavard, who was a great champion of decimalization. He persuaded the other members of the commission that the meter should be 1/10,000,000th of the distance from the North Pole to the equator on a meridian passing through Paris, not Greenwich. That should have made the polar circumference of the globe 40,000 kilometers. This was a bad time to go surveying in France, given the start of the Revolutionary Wars, when Napoleon kicked the crap out of Austria, Spain, Belgium, the Netherlands, Germany, and Great Britain combined, together with Portugal and much of Italy. France won, although we, Great Britain, did not accept this and went on fighting. To this day, if all tales be true. If you add in the Terror and the Napoleonic Wars, plus they had to go over the Pyrenees into Spain for the last leg, you will understand why the distance from the pole to the equator ended up a little bit off, at 40,007 kilometers. But with each meter perfect to within 4 tillibits of an ujar for the ratio of the 2 states of nuclear energy. What a coincidence. And they're at it again. Last month, on Friday the 16th, the 26th meeting of the Conférence Générale des Poids et Mesures, this time in Versailles, voted, among other things, to redefine the kilogram in terms of Planck's constant. You will note our old friends, the second and the meter squared, as well, at least implicitly, as its baby cousin, the cubic centimeter, which originally defined the gram and thus the kilogram. At this point, one or two of the more suspicious amongst you might be wondering if perhaps the system isn't simply measuring itself in some peculiar way. It would certainly explain the levels of accuracy. However, people like Stephen Hawking and of course Einstein vouch for the validity of their work, so even to suggest such a thing would therefore imply that all mathematics, and thus all mathematicians, are delusional. Unreasonably effective maths may be, but I can't believe that. Nor can I believe that humans designed the universe, even though mathematically that is the simplest solution. All you have to do is believe in what is called the block universe, in which time travel is possible, and a lot of people have believed in that, including Einstein. Plus, there's definitely a movie in it. However, in the end, as far as I can see, it all must just be a huge coincidence. Or not, of course.
Wow. So there we are. Now, does anybody on this stage in the evening in a Bavard bar? I throw I throw it over to you to ask questions about Bavard if you wish. It's way above my pay grade. I'll be entirely honest with you. But look, there's a question already, so I'm going to come over here. Steve.
Did Napoleon kick the metric or imperial shit out of everybody else?
There we are.
He kicked the shit out of the metric and reinstated what he called the usual measures. So that was fine.
Any other questions for David? And there's a yeah.
David, could you apply your constant there to the question of when I'm going to visit my granny in Bristol on the M4, taking into account the possible traffic, how long will it take?
That's not the problem. The problem is that your question then goes 24,000 miles up and 24,000 miles back at huge speed, which of course affects the answer. And if you don't allow for that, you end up in Bathurst.
Any other questions for David? And anything Einstein or E equals mc? You want? Yes, a hand over here. There's a hand over here. Yeah, right. Here we go.
Cheers, thank you. I realise I might come over as ignorant here, but I've always wondered why is there a correlation between bound and unbound energy and the speed of light? Why not sound? Why not some other form? Was that discovered, or was it like you seem to suggest?
Really, that is Einstein's great contribution to everything, is that he, just working from principles alone, not so much with the maths, he wasn't that great at the maths, but just working from principles alone, he established that this formula would work, and would work everywhere. It's a fundamental formula of the thing, because it has neither E nor M are specified. They don't have to have specification. It's only the relationship that is specified. And working from there, then it's quite easy to get into relativity, and then general relativity, and eventually quantum. Of course, that's where Einstein got off.
Any other questions? Any other questions for David before we then? Yes. Oh, hands here. Right. Let me.
Hi. So if it's a constant speed of sound, does that mean it's impossible to go faster? Sorry, speed of light. Does that mean it's impossible to go faster than the speed of light?
That isn't the direct connection, but it is impossible to go faster than the speed of light, because the speed of light is also the speed of all electromagnetic, and most importantly, the speed of causality. You can't exceed the speed of causality.
There you are. Well, I think that's a cracking note to end on. See? Oh no, there's one more question. I'm going to take. Hang on, David, can you stay there? You see how much we learned about Bavard? There was a hand. David, yes.
I've always been struck by the idea that a photon of light exists outside of time because it travels at the speed of light. It doesn't. I would have thought, under my understanding of the aging process, does a photon age because it exists outside of time.
Yes, there's a thing called the C paradox, which is that obviously a photon travels at the speed of light. But if you do the maths, light doesn't travel at that speed, it's already there where it's always been.
Have you just developed an anti-aging formula for us? Because I didn't quite get it, but I think that might have been what you said. Yeah?
No, it is interesting because, of course, the C paradox shows why it's possible to get something from nothing, because it's still nothing. The Hamiltonian of the universe is zero. So none of this is actually real.
Well, that's... See, I did say it was above my pay grade. It's way above, but it's wonderful. Does any final questions for David before we take... Oh, hang on. Right, back over here. See, it is an audience full of physicists, David. Where was the hand? Yes.
I'm sorry, I'm not a physicist. In fact, I have the greatest suspicion of Einstein and his abilities. To tell you a little anecdote, he was a keen musician, as you probably know, keen violinist, and he used to play with the very famous virtuoso of his time, Jascha Heifetz. And frequently, Einstein didn't do quite as well in the playing as Heifetz did. And on one occasion, Heifetz exasperatedly said, "Can't you count, Albert?" And so I'm advanced this as a possibility as to why sometimes these things may be disjusted.
Thank you very much. David, do you want to respond on that?
No.
No, we're happy. We'll leave that where it is. There was another hand, I've come away, but there was another hand, I thought. Did I see a hand waving? Yeah, someone's pointing, I can't. Ah, yes, over there. Right, okay. This may be the final question.
Hello. I've always wanted to know if E equals mc squared is really the most beautiful looking equation for us.
Well, I showed you how Einstein wrote it. This time it didn't look fabulous, did it? But in terms of its simplicity and its power, it is absolutely the most beautiful equation.
There we are. Well, can we... Oh, hang on, there's another... Oh, sorry. You haven't said this isn't real, have you? Did I miss that bit?
No, yes.
You did say that. I missed that.
It is... this is what reality is, but in the end, if you do the maths...
There we are. Well, can we have a huge... can we have a huge round of applause for David?